morning to all. So we are getting into this fresh week of classwork. I guess in about 2.5 weeks or 2 to 3 weeks time, you will have your CAT 1 examination. Okay, so for CAT 1 examination, the portions are Module 1, Module 2, and part of Module 3. Okay, so to the extent what we will be covering, I will be you'll be having that for the exam. In the meantime, I will also try to arrange a guest lecture. Somebody from industry will come and talk to you about some practical application of heat transfer. I expect it will be in electric motors, but I will have to check. So that's a current trending topic. So it will be useful for you because it's very much relevant to this particular course. Also, the assignment, digital assignment 1, in maybe in 1 week or 10 days, I will post. I think LMS is not working, right? Moodle is not working. Have any other faculty used Moodle for you?
No, sir. Teams.
Yeah,
No, sir.
Moodle is not working, so I will have to do it. Whatever assignment I give, I will have to do it in Teams. I will do that. Okay. So I will take the submission in Teams itself. If it is not yet ready within 10 days time. Okay. So as far as today's agenda is concerned, I will continue with the theory. A little bit of theory is there left, and then I'll take up a couple of problems also. So in the topics that we have covered, we'll solve problems. So in today's class, partly tomorrow's class, and also on Thursday's class, we will solve some numerical problems related to heat transfer, module 2. So I want you to be prepared, come prepared to the class with a notebook, a calculator, heat and mass transfer data book. That's extremely important. And also, of course, a pen. Okay, so for this class, what we'll do is we'll take up the next topic. But before that, I would like to recapitulate what we have seen until now in this particular module. What we have seen is the general conduction equation. So what we have seen is that we can derive this general conduction equation in 3 coordinate systems: Cartesian, cylindrical, and spherical coordinate systems. I have shown you the detailed version of the Cartesian coordinate system derivation. So you will have to bring in concepts of calculus, concepts of energy balance. So thermodynamics comes into picture, mathematics comes into picture. And if you are to do a similar balance with convection involved, you will also have to bring concepts of fluid mechanics. But as of this module, that won't be needed. Okay. So we brought in concepts of thermodynamics, concepts of mathematics, and performed a heat balance on a cubical element or a cuboidal element. And we have used the general equation, general balance equation, saying that whatever goes in minus whatever comes out should equal to whatever accumulates. That whatever can be mass or can be energy. In this case, it is heat energy. So using those concepts, we could come up with a general heat conduction equation in Cartesian coordinates. We have also seen some special cases of those of that conduction equation where we could reduce it to instead of unsteady state, we can reduce it to steady state. Instead of having variable conductivity, we can take it as a constant conductivity. And instead of having a multi-dimensional effects, we can reduce it to one-dimensional effect under certain circumstances. Not every problem can be simplified. You will have to, in some very general cases, you will have to deal with all 3-dimensional transient with heat generation and with variable properties. So that will be a very general problem, and only software packages will be able to solve that, which use basically finite difference methods, finite volume methods, and so on. So CFD packages like Fluent is one solution, is one application which does that such kind of solutions. But to obtain closed form solution or analytical solution, we will have to simplify that, because for complicated equations, the analytical solutions are not available, are simply not available. There's nothing we can do about it. So what we have seen as a part of this course is that we considered some special cases where there is no heat generation, there is a constant thermal conductivity, there is no transient system, and there is also no multidimensional effect. So we considered certain cases with one-dimensional effect having constant temperature boundary conditions, and we derived some temperature profile of a rectangular slab, a cylinder, and a sphere. Likewise, we did some other cases. So now I will project what we have done. I have summarized all that in one single slide. So I will project that, and this is kind of a summary of what we have been doing all these days. So as I said in one of the earlier classes, any heat transfer problem will have to determine what will be the amount of heat transferred and what will be the temperature distribution. So these are the two important questions to be answered. What is the temperature distribution? So at any location, at a given location, what is the temperature? And also what is the amount of heat transferred? So these things you will have to find out. So you have these equations here. So this is the general heat equation in one-dimensional steady state with no heat generation. You see, we have reduced it to the least complicated situation here. So if you consider this for a plane wall, this will be the governing equation. This will be for the cylindrical geometry, and this will be for the spherical geometry. Okay, and what will be the temperature distribution? This will be the temperature distribution in the wall. Ts1 is the temperature at the surface, and delta T is the temperature difference. X is the distance at which you want the temperature. So this is the general temperature distribution equation. You can plot it for x varying from 0 to L and get a straight line. You can see this is a straight line. Now here you can see in this profile, you see there are logarithms. That means it is non-linear. Here also in spherical also you will see it is a non-linear. Okay. Then you see here the heat flux. We will also be interested in heat flux. So in heat, this is the equation for heat flux. But if you know the rate of heat transfer, if you know this equation, you can very well derive the heat flux. So you don't have to memorize. In fact, if you have that data book, you don't have to memorize anything. And we also introduced the concept of the thermal resistance. So we saw that there is an analogy between heat transfer and the flow of current. So current is similar to heat. Temperature difference is similar to potential difference. And therefore, electrical resistance is similar to the thermal resistance. So the thermal resistance we could derive for conduction, for convection, and also for radiation. But for a plane wall, the conduction resistance is L by Ka, and for cylindrical wall, this is the equation, and for spherical wall, this is the conduction resistance. Convection resistance, we know 1 by Ha is the convection resistance, but anyway, in this particular situation, convection is not coming. So this is the summary of some of the equations under very, very special conditions. Okay, so these are not general, but applicable only for these conditions. Now we have also seen what is the concept of critical radius of insulation. So when I say critical radius, it is not, or it is different from optimum radius of insulation. Optimum radius of insulation is something which maximizes the insulation. That means which reduces the heat transfer. But critical radius of insulation is something that maximizes the heat transfer or minimizes the thermal resistance. And we have seen this to be applicable in curved surfaces only, not on flat surfaces. So in case of cylinder and sphere only, we will have this concept of critical radius of insulation. In case of rectangular slabs, there is no concept of critical radius of insulation. And we have seen that we have derived this equation. The critical radius of insulation for a cylinder is K by H. And I have also given this equation for a sphere, it is 2K divided by H. And you can find these equations in the data book. I gave you the page numbers. Now coming to making things little bit complicated. So you see here, this is one-dimensional steady state with no heat generation. So what we'll do is we will consider one-dimensional steady state with heat generation. So we will consider the heat generation. That means you see in this equation, d square T by dx square, additional to this term, there will be a heat generation term. Heat generation term is represented by Q dot. So that Q dot will appear in this equation, and in this equation also. So when heat generation takes place, what will be the temperature distribution inside a solid surface? That solid can be a rectangle, a sphere, or a cylinder. So what will be the temperature distribution, and also what will be the heat transfer? So these two questions we'll try to answer by including the heat generation. So 1D steady state with heat generation. Now what is the importance of this? Thermal energy generation is observed in electrical conductors due to ohmic heating. So this is known to us. When a current passes through a conductor, some heat is generated, and that heat generated using the parameters of electrical engineering, we can compute it as I square R. I is the current and R is the resistance. Current in amperes, R is in ohms. Okay, so this Q dot is the heat generated is E dot divided by V, or I square R by V. So this is V is not voltage. Remember, V is volume. So in heat transfer, it is convenient to deal with the heat generation per given volume. Okay, so we use this. So I square R divided by V. This is the volumetric heat generation. So usually, whenever we deal with heat generation, it is considered in I can say mechanical engineering. You always treat it as a volumetric phenomenon. It is not a surface phenomena. It's not a phenomenon that depends on the area. It depends on the volume. Therefore, heat generation is always a volumetric in nature when quantified. So this is how we use it. Q dot is the volumetric heat generation measured in watt per cubic meter. Now, there are other examples also where heat generation takes place. Heat generation also occurs in nuclear reactors during deceleration and absorption of neutrons. So, there is heat generation taking place. So, when this heat generation is out of control, when the temperature rise inside a nuclear reactor is very rapid, then we will have this nuclear station accidents. Also, heat generation occurs during exothermic reactions. There are chemical reactions where there is a heat generation taking place. So, in nuclear reactions, in chemical reactions, in electric conductors, we have this heat generation. Now, before we proceed to the next slide, I would like to clarify that heat generation doesn't always be or doesn't always necessarily result in increase in temperature. So especially when we deal with the mathematical form of this heat generation from Q dot, it doesn't have to be always resulting in rise in temperature. It can also result in drop in temperature. Now in such a case, we will call it heat consumption. In reality, to be more correct, we should be calling it as a heat consumption. So this Q dot, as it appears in the equation that I'm going to show you, that Q dot can be positive or can be negative. If it is positive, you will have to take it as a heat generated, which can result in increase in temperature. If Q dot is negative, then it can be heat consumption, which can result in drop in temperature. Okay, so this Q dot doesn't always have to be a positive term which results in increase in temperature. It can also be the other way around. Still, the treatment is the same. For example, if I want to include heat generation, I will add plus Q dot. If I have to consider heat consumption, I will have to add minus Q dot. So in that way, I will have to take care of the phenomenon. Now we will consider one example. 1D steady state with heat generation in a plane wall. So we have seen this plane wall geometry before. We found out the temperature distribution inside a plane wall without heat generation when the two extreme wall temperatures are given. Okay. Now, so same thing we are taking up once again, but now we will include heat generation. Now, for the sake of clarity that will come up in the subsequent slides, I would like to point out one difference between the geometry that you are seeing here and the previous geometry that we have seen earlier. In the previous geometry where we derived the temperature distribution in a plane wall, x was measured from this point. So here on the left side x is equal to 0 and on the right side x is equal to L. And here I had TS1, here TS2. Okay, the temperature distribution was something like this. Now the geometry we are considering here is the same. It's very similar, but except the measurement direction is different. Now the measurement of x is at the mid plane. You see here, this is the mid plane, and towards the right side, x is positive and towards left side x is negative. So this is for the sake of convenience and nothing else. Okay. So you will see why this is convenient later on. Now you see there is a slab here, and this slab has a one temperature Ts1 on the left face, one temperature Ts2 on the right face. As of now, let us ignore the convection part. That means we are restricting ourselves to the solid portion only. And there is also heat generation here. So when there is heat generation, what will be the temperature distribution? Again, to solve this problem, this is a one-dimensional steady state problem, but with heat generation. So when we say one-dimensional, then the y and z terms will vanish. Steady state means dou t by dou tau will vanish. What remains is this equation, dou square t by dou x square, and q dot by k will come. This will take care of the unsteady of the heat generation. So earlier when there was no heat generation, this was the only equation. Now with heat generation, we add this. So here q dot is taken as a positive quantity. It can also be negative. That we will call that as a heat consumption. Okay. Now let us look at this equation. So the first term, dou square t by dou x square, is the heat conduction term in the x direction, and this is the heat generation term. There is on the right hand side we have 0. That means this transient term dou t by dou tau is equal to 0. So this is the steady state term, dou t by dou tau is equal to 0. That's why right side is 0. Now if you look at this equation, this is basically a second order ordinary differential equation. The temperature is varying only with x. There is only one independent variable. Therefore, this is a ordinary differential equation. So instead of dou t by dou x, we have written as dt by dx. But it's a d square t by dx square because this is an ordinary differential equation. And since it said second order equation, that the two squares are there. No, these squares imply that this is a second order. Then for second order equation to get a solution, we will need two boundary conditions. One boundary condition, because why two boundary conditions? Because since this is d square t by dx square, as a part of the solution, you will have to integrate twice. When you integrate twice, you will get two constants of integration. To evaluate those two constants of integration, you will need two boundary conditions. We already have these two boundary conditions, the temperature on the left hand side and the temperature on the right hand side. So this equation, if you integrate it once, this square will go. What remains is dt by dx is equal to, now this q dot by k will go to the right hand side. This will be minus q dot by k x plus a constant of integration c1. Then further integrating this dt by dx, now we can actually separate the variables, keep dt on the left side, dx to the right side. Then on integrating you will have, so on performing this integration, you will have, on integrating dt you will have t, on integrating minus q dot by k x with respect to x, you will have minus q dot by 2k. Q dot is a constant, the heat generation term is a constant, k is a constant, thermal conductivity is a constant in this case. So x is only variable, so integral x dx is x square by 2. So this 2 will come into picture. Plus on integrating c1 we have c1x, and since we are integrating again, there is a second constant of integration c2. So now we have two unknowns, c1 and c2. So to evaluate these two unknowns, so we will need two equations. So the two equations are like this. At t is equal to minus L, T minus L, the temperature is Ts1, this one. And at T is equal to L, so on this side, L means plus L. At T is equal to plus L, the temperature is Ts2, this temperature. So these two conditions, if you substitute here, you will get two equations, and with those two equations, you will be able to solve get the values of C1 and C2. So you can do that on your own. Then you will have C1 as Ts2 minus Ts1 by 2L, and C2 as Q dot by 2K L square plus Ts1 plus Ts2 by 2. So this two, if you substitute here, you will get the temperature distribution. inside this. Now you can see here in this equation, this is a linear term. It's only x, but here you see there is a x square. This is non-linear. That means the temperature distribution inside a plane wall with heat generation is non-linear. So you can see here, this temperature profile is actually increasing and then dropping. So that is because of this non-linearity, and that is due to this heat generation term. So this is the temperature distribution that is inside a plane wall with heat generation. Now you will find this equation in page number 56. This is in data book, page 56. The notation can be different, but this is the same equation. Okay. Now we'll move on to the slide, a special case of the previous one. Now here you see in this case we have taken two different temperatures on the left and right side. Now one special case is that special case is basically useless in case of in this particular case, but in case of heat generation it is making sense. What is that? In a plane wall, when the temperatures are symmetric, when the wall temperatures are the same, that means the left side wall temperature is Ts, right side wall temperature also is Ts. So in fact, Ts1 is equal to Ts2. If we equate it to Ts, then what will be the temperature distribution? So what we have to do is, in this equation, you substitute Ts1 and Ts2 as Ts. So since Ts1 and Ts2 are same, this term will go, so entire term will be 0, and Ts1 plus Ts2 by 2 will be simply Ts, because Ts plus Ts, that is 2Ts by 2 is simply Ts. So you will have this term and this term. So the temperature distribution inside a plane wall with equal wall temperatures with heat generation is this equation. So this term takes care of the heat generation, and this one is the wall temperature. Now you can see again in this there is x square, which makes it non-linear. So if you try to plot the temperature distribution in this, you see this is the kind of temperature distribution you get. So you can see that there is actually a peak. So that means in this plane wall, this is kind of a parabola, a symmetric parabola. Okay, so if you take the slope at this point, can you guess what will be the slope here at this point? dt by dx. What is the slope here?
0.
The slope will be 0, because you see there is a mirror image on both sides. Therefore, the slope has to be 0. Now, this particular concept is taken as an advantage in computational fluid dynamics, in systems where there is a symmetry. You see here these two are symmetric. Why? Because the temperatures are same on the either side. So if you want to make computations in this in computational fluid dynamics softwares like Fluent and so on, what we do is, instead of taking the entire domain for the computation, you take only half of it. Only half. We calculate, we do the computations only in this, and we say that whatever is on the right hand side will be a mirror image of whatever is on the left hand side. That's called as a symmetry condition. So such an advantage is possible in this case. Now at t is equal to 0, at temperature at x is equal to 0. So at the mid plane, if you substitute x is equal to 0, you will have this equation. Now for this particular case, the temperature distribution, if you try to evaluate, you will get this as the temperature distribution. Now this is meant for a symmetric condition, symmetric wall temperatures only. So this equation is available. It's available again in page 56, data book, page 56. Okay. Now you can see here the effect of dt by dx is equal to 0 is shown here. At the mid plane, dt by dx is equal to 0. So you see here, when dt by dx is equal to 0 at mid plane, what will be the value of q? Q is equal to minus Ka dt by dx. Now, if dt by dx is equal to 0, because this is at the peak and this is symmetric, dt by dx will be 0. So, since this is 0, Q will be equal to 0. When Q is equal to 0, what is the name for such a system? When there is no heat transfer, there is a name, no?
So adiabatic.
It's adiabatic. Adiabatic means no heat transfer. That means the mid plane is a kind of adiabatic. It's not intentional, but it acts as an insulator. So it acts like an insulated surface. Therefore, you see at the center, this kind of a dots are shown to represent the insulation. So this is insulation, so no heat will pass across this. So at this point, we can treat it as a adiabatic wall or a adiabatic boundary condition. Okay, so this is something you need to understand, and all these things are true for symmetric boundary conditions only. If you take the previous case here, in this case, that thing will not apply. That will apply where at one point where dt by dx is equal to 0 at this peak. So the peak in this case is different from the peak, and in this case the peak occurs at a different physical location in these two different cases. And at that particular point of the peak where the slope is 0, we can say that the heat transfer is 0. Now there is one more condition to take place. You see here in this particular figure, I told that at the moment we'll ignore this convection. So if we consider convection, we will have some tool, some means to estimate the surface temperature at the point if we don't know the surface temperature. So what we do is we'll try to implement the convective boundary condition at the wall. You see here there is convective boundary condition at the wall. Now if you look at this, you have both the wall temperatures equal and the fluid temperature is T infinity here and here. The heat transfer coefficient is H here and here. Therefore, this is basically symmetric along this mid plane. Okay. So let us consider the convective boundary condition on one side. So whatever is true on the right side will also be true on the left side. So whatever is valid on the right will also be valid on the left side. Now to do this, or this is called as implementing the convective boundary condition. So at this boundary there is a convection taking place. To implement the convective boundary condition, what we have to do is we take this region and perform an energy balance. This is the control volume and we perform an energy balance. That control volume in this figure is represented as this dashed line. So what is happening in within this control volume? This control volume is comprising partly on the left side, it is comprising of the solid part, and on the right side it is comprising of the gaseous part. So in the solid part we know conduction takes place, and in the gaseous part we know convection takes place. So what is happening within the control volume is some heat is conducted into the control volume and the same heat is convected out of the control volume. Why I am saying the same heat is because we are currently dealing with a steady state. So under steady state conditions, there won't be any heat accumulation. Therefore, whatever enters must leave. So whatever enters this control volume must leave it. But the mode of entering the control volume is by conduction, and the mode of leaving the control volume is by convection. So that's the difference. So what we have to do is we have to equate this conduction heat transfer to convection heat transfer. So that is what exactly we'll be doing it. Now you look at this equation. Minus k dt by dx at x is equal to L. What is x is equal to L? This one, this region, this outer boundary on the right is x is equal to L. X is equal to minus L is here. So because it's not convenient to deal with negative signs, we'll keep it simple. Deal with the positive sign. So x is equal to L. We try to evaluate the heat conducted. Now is this heat conducted? Minus k dt by dx, is it heat conducted? What is this quantity? If you evaluate, what will be the unit of this particular quantity? This is heat flux. Watt per meter square. Because we have removed that area term here. There must be area here, there must be area here. Both these terms have been cancelled. So what we have is the heat flux on the left side of the control volume should be same as the heat flux on the right hand of the control volume. But heat transfer on the left side is due to conduction, so we use the conduction equation. On the right side it is convection, we use the convection equation. So minus k dt by dx at x is equal to L is equal to h multiplied by Ts minus T infinity. Ts is the surface temperature minus T infinity. So from this we can obtain the this value we need to evaluate this particular equation. Dt by dx can be obtained from the temperature distribution. We have this temperature distribution previous slide. So this is the temperature distribution T as a function of x. So dt by dx can be obtained by differentiating this equation. So we have this equation, we differentiate that dt by dx will be minus q dot x by k. Okay, so now dt by dx at x is equal to L. When you replace x with L, you will have minus q dot L by k. So this and this are same, except x is replaced with L. So dt by dx at x is equal to L is minus q dot L by k. So that you substitute here. Then you will get, if you and once you substitute and try to evaluate the value of Ts, you will get Ts in this manner. You will get the value of Ts like this, you can compute it. So if you do not know the wall temperature, but you know that it is symmetric, then using the convection conditions, you can estimate the wall temperature. Now, where do you find this equation? This equation is again found in page 56 of your data book. Okay, the nomenclature is slightly different. There in the data book it is given as Tw is equal to T infinity plus Q dot L by H. So I called it Ts. The data book is calling it Tw. W stands for wall. Okay, this is about the slab. Now what about the cylinder? Now for the cylinder also things will be very much similar. You see, for in the equations for a cylinder, this is the heat conduction equation without heat generation and in one dimension and no generation. Now we will have to include the generation term. So what we do is we bring in the generation term here. So in that equation we add q dot by k. Okay, before going into this term, I just want to clarify about one thing. Suppose this heat generation is negative in this case, then let us say this surface is both surfaces are temperature Ts. Then the temperature distribution, if the heat generation is negative, the temperature distribution will be something like this. Temperature will drop and then increase. So here in this same figure, if I want to plot, it will be like this. Okay, so this will be the temperature distribution or the temperature profile when the heat is being consumed, not generated. Okay, now coming to the geometry, cylindrical geometry. Here we have, this is the one-dimensional conduction term, and then we have this heat generation term. Again, the boundary conditions are at R is at the center, let us say at the center point, dt by dr is equal to 0. Now, how did we get this? dt by dr is equal to 0. Can somebody tell how we got this boundary condition? Now remember, this is not a cylindrical shell, this is a solid cylinder. The outside temperature at T is equal to T is equal to Ts at RO. RO is the outer radius. So this is the outer surface. On the surface, the temperature is Ts. But at the center, at R is equal to 0, that is at the center, dt by dr is equal to 0. Now this condition comes from the symmetry. You see here, this is the cross section of a cylinder, and then you see here at the center, things are symmetrical. Things are symmetrical. So whatever is happening in this side will also happen on this side. Whatever is happening on this side will also happen on this side. Whatever will happen on this side will also happen on this side. So things are very much symmetrical. This and this are symmetric, this and this are symmetric. So in fact, by taking the advantage of symmetrical conditions in computational fluid dynamics, instead of making computations all over this surface, we take only one region. So we compute only in one region and apply the symmetric boundary condition on this wall and on this wall. So basically what I am trying to say is at the center point, the condition is dt by dr is equal to 0. Why? Because of symmetry, and symmetry means insulated condition, adiabatic condition, therefore no heat transfer, therefore no thermal gradient at that point. Okay, so this is one condition and this other condition available, and this also is a second order ordinary differential equation. So we need two boundary conditions. So we have two boundary conditions, this one and this. So to solve this, we'll have to differentiate it two times. So once you differentiate it two times and evaluate the constants of C1 and C2 and substitute, you will get this. So the derivation I'm not showing. The integrations and all are similar, are simple, and I know you are very good at this integration. So you fill in the blanks. You integrate this twice, you will get this C1 and C2, apply these boundary conditions, and you will get this equation. So using this equation, you can also apply the boundary condition, the convective boundary conditions we use here. We use for the case of this plane wall, and you will get other equation relating the surface temperature to the convective heat transfer coefficient at this point, this value. Okay, so these two can be derived, and also you can find out what is the heat transferred. Q is equal to either you take a control volume on the surface and apply the same condition, heat conducted is equal to heat converted. You will be able to find out what is the heat transfer. Next we have this sphere. The condition for the sphere is, you see again, this is the one-dimensional heat transfer or heat conduction equation for a sphere. To this, on the left hand side, you add Q dot by K. That will take care of the heat generation, and you will be able to solve it. The conditions, boundary conditions for the sphere also are similar to that of a cylinder. The boundary conditions are dt by dr at r is equal to 0. This will be equal to 0, and T is equal to Ts at R is equal to R out. So this is the R outer, this is the temperature. So this is one thermal boundary condition. This is the Dirichlet boundary condition. On the surface we know the temperature, so it's called as the Dirichlet boundary condition. At the center we are given this dt by dr, the thermal gradient. What is the name of this boundary condition? You have seen this earlier. What's the name of this thermal gradient boundary condition?
So conduction.
No, there's a name. It's a name of some scientist. When surface temperature is given, the boundary conditions, when given temperature is given, the name of that boundary condition is Dirichlet boundary condition. When the gradient is given dt by dx or dt by dr, this is given, what's the name? It's a Newman boundary condition. Okay, so you need to remember this. Now, where do you find this equation? Which page in the data book? You will see this equation in page number 57. Page 57 of the data book. So I want you to refer. See, it's very important that you get yourself familiarized with the contents of the data book. Otherwise, it becomes extremely difficult for you to follow. And it's impossible to remember all these things. And if you are searching in the examination, if you are searching for the appropriate equation, see, the equation will be there, and equation needs to be applied under certain conditions, and there is a certain nomenclature for the equation. So you should make yourself familiar with the location of the equation in the data book, what are the conditions at which it is applicable, and also the nomenclature of the data book. So what I call in the slides, what I call TS, in the data book it is called as a TW, T-wall. So that you should be very much familiar even before the examination, so that you should not waste time in figuring out what is the similarity between TS and TW. Okay. So I will leave it at that. That's it. That's about the theory. We have some problems, and as of now, I think we don't have enough time to take up a problem, but just we'll look at this problem. How many of you are familiar with surface plots in MATLAB? Anyone knows how to plot a surface in a MATLAB? (3D) surface plots. You see here, in this problem, we are given some temperature distribution on a 3-dimensional surface.
That's surf command.
Sorry?
SURF command.
Louder, I'm not able to get you.
So there's a command SURF.
Surf, okay.
That
Surf,
creates
3D surf. So basically, you should provide the coordinates. You should tell X is ranging from what to what, Y from what to what, Z to what, and then you will have to come up with a network matrix. And at that matrix, you will have to compute the temperatures using the temperature profile equation given. Anyway, that's a different topic. I just digressed. Now, look at this problem. At a given instant of time, the temperature distribution within an infinite homogeneous body is given by the function. This word infinite will have, it has got a heat transfer meaning. So don't go by the English meaning, don't go by the literal meaning, then it has got infinite, it has got a heat transfer meaning, which we will see in the next module. Okay. So as of now, don't bother about this word infinite. Infinite homogeneous body. Homogeneous body means having the same material throughout. That is given. The temperature distribution is given. So temperature as a function of x, y, and z at a certain point of time is given as this coordinates of x, y, z, the values. So at different locations, if you substitute the value of x, y, and z, you will be able to calculate the temperature. So if you imagine a 3-dimensional region, every point will have 3 coordinates. So you substitute those 3 coordinates and you will get the temperature at that particular point. Likewise, if you discretize the entire 3-dimensional region into some a finite number of points, you will be able to find the temperature at each and every point. Then you will be able to plot a surface plot on that. Okay. Now we are asked a question. Assuming constant properties and no internal heat generation, determine the regions where the temperature changes with time. We are asked to find what are the regions where the temperature changes with time. That means we are basically asking, since we have a temperature distribution, we want to know whether it is a steady state or transient. Steady state or transient. So that is the question being asked in this particular problem. Okay. So for that, what we have to do basically is we'll have to evaluate the value of dou T by dou tau is how much. If this dou T by dou tau is equal to a positive quantity, we can say that the temperature is increasing or it is increasing with time. If this quantity is negative, we can say that the temperature is decreasing with time at a particular location. And if it is 0, that means this temperature is not changing with time. So the answer for this question lies in estimating the value of dou T by dou tau. So once we know the value of dou T by dou tau, we will be able to tell whether there is a change in time, change of temperature with respect to time or not. So that we will solve in tomorrow's class. So in tomorrow's class, we'll take up a few problems and work them out. So for tomorrow's class, come prepared with your calculators and data book. Now I'd like to stop here and take your attendance. Mrutunidhi?
Present, sir.
Ancharian?
Present, sir.
Madhusudan? Pranav Dilip?
Present, sir.
Siddharth?
Present, sir.
Watson, Prem,
Present, sir.
Ganivel,
Present, sir.
Kalagan, Niranjan,
Present, sir.
Vaibhav Karan,
Present, sir.
Krishna,
Present, sir. Abhijit present, sir.
Present, sir. Present, sir.
Praveen,
Praveen present, sir.
Adil Sinju,
Present, sir.
present, sir.
Chaturvedi,
Present, sir. Present, sir. Chindan present, sir.
Hamza Hassan,
Sir, Hamza Hassan present, sir.
Present, sir.
Madan,
Present, sir.
Hemant Kumar,
Yes, sir.
Vishwa,
Present, sir.
Chandramouli Pratap Singh, Shubh Vania,
Present, sir. Present, sir.
Sai Rohit,
Sir.
Sri Raman, Vishal, Deepesh,
Deepesh present, sir.
Anirudh Venkat,
Yes, sir.
P. Kumaran,
Present, sir.
Sri Raman. Sri Raman, wait for the next round. Okay. Sundar Krishna, Pranav,
Present, sir.
Jayanti,
Present, sir.
Niket,
Present, sir.
Badri Narayanan, Ajit,
Present, sir.
Raghav,
Yes, sir.
Rahul,
Present, sir.
Rose,
Present, sir.
Bihar,
Present, sir.
Present, sir.
Gauri Shankar,
Modi, sir. Present, sir.
Jay Prakash,
Yes, sir.
Suja,
Suja present, sir.
Kumar, Karan Sarvesh,
Present, sir.
Ajay,
Present, sir.
Benol Simon,
Present, sir.
Vamsi Krishna, Venkatesh,
Present, sir.
Yanakshaya,
Present, sir.
Dev,
Present, sir.
Arun,
Present, sir.
Kunal Rao,
Kunal present, sir.
Vignesh Krishna,
Yes, sir.
Vedant Madhur,
Present, sir.
Swanand,
Present, sir.
Ani,
Present, sir.
Vasan,
Present, sir.
Present, sir.
Sir, I present, sir.
Anish,
Is present, sir. Santosh, sir. Present, sir.
Keshav Kumar,
Present, sir. Present, sir.
Kartik Prasanna,
Present, sir.
Kaustubh,
Present, sir.
Varun present.
Sarvesh Krishnan,
Present, sir. Present, sir.
LC Femina,
Present, sir.
Effort GNL,
Present, sir.
Amal Manoj.
Present, sir.
I'll quickly call the absentees. Madhusudan,
Present, sir.
Srivatsan,
Sir.
Srivatsan, Palanivel. Palanivel. Tamilalagan.
Present, sir.
Sri Raman.
Present, sir.
Sundar Krishna. Badri Narayanan. Avito.
Present.
Who is that?
Sir, Avito.
Your voice is very low. What's your name?
Sir, Avito present.
Avito. Okay. Gauri Shankar.
Present, sir.
Prem Kumar.
Prem Kumar is separate in chat box, sir.
Sri Krishna. Kalai Priyan.
Sir, present, sir.
All right. So we'll meet tomorrow at 8 o'clock. Now you can leave the class.
Thank you, sir. Sir,
Thank you, sir.
Yes, yes.
sir, actually, I had a lag in my laptop, sir, so I was unable to give my attendance, sir. Now only I rejoined, sir.
What's your name? What's
Vamsi Krishna, 19 BME 1262.
post it here. I will mark you.
Okay.
Post a message.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Sir?
Yes.
Sir, this is Sundar, sir. Sir, actually, I was present and I was telling, but my mic was not working, sir. So
Okay.
you
Yeah,
couldn't say.
I saw that. Okay.
Thank you, sir.